So the exam preparation materials are up. You can find them here at Course Content, Exam Preparation. There's two things, the FAQ that talks about what's on the exam and what the format is going to be. Hint, 38 questions, 30 questions, multiple choice. Use the Scantron, so bring a pencil. I don't bring extras because, bring a pencil. And the topics of interest. The stuff that is on the topics of interest will show up on the exam in some fashion, either as a question or as an answer option. Stuff that is not on the topics of interest will not show up on the exam. Okay, so that's how that works. And we'll talk a little bit more about that with the few minutes we have left at the end of the session. So anyway, so where we left off was here. We had just finished up talking about auto-sizing and ads and clickbait stuff. And now we're going to get into some of the more technical details, like content management systems and cloud systems and ACID properties. So, and some other things. So we'll go ahead and get in on that. So first question, what is a content management system? Well, a content management system is a system that has two elements. Number one, a content management application. So by content, we mean all the stuff that you can see. So on Facebook, for example, content would include people's posts, would include ads, would include notifications from Facebook, instant messages, all that kind of stuff. Everything you might look at on Facebook, that's what we mean by content. And you need tools for adding it, for changing it, and deleting it, right? You post something, that's adding content. You don't like the way it looks, you edit it, and that's changing it. And you say, I probably was drunk when I posted that. I should just take that down entirely. That's deleting it. Okay. And of course, there's the content delivery application. So content delivery means all the tools for permission-based content distribution. Basically, who gets to see what, and making sure that it happens reasonably quickly. So Facebook feed is what you might call a semi-public content management system. So a fully public one, everybody could see everything. And a fully private one would mean basically you could only see your own stuff. So a simple example there would be something like a banking application where obviously you don't want other people to be able to see your account details. Facebook's kind of in the middle, right? The default setting is that people who are your friends can see your stuff, right? But you can have more or less restriction around that. You can set up posts to show them to the entire universe, or you can set up posts to show only to a small subset of your friends, or in fact, only to yourself. So, of course, users want to manage those controls. Businesses generally want to show everything to everybody, unless they're paying for it, right? If businesses are paying to show ads, of course they want to limit it to users who are likely to be interested in what they're showing. They don't want to have to pay for accidental clicks. And of course, Facebook, if Facebook has a notification, that pretty much goes to everybody on Facebook. It's like, here's something you should know. Okay. So content delivery is based on user influence rules. There are certain things that you have influence on. For example, you can deliberately say somebody can or cannot see a post you made, but you also have some latitude to control what you see on Facebook just by what you click on. For example, there was a window about, it was about 5 years ago or so, where my wife started reading some horrible articles about, Illinois cases of child abuse. And she ends up going down this rabbit hole of reading like a bunch of horrible things that have happened. And then because she did that, Facebook for a long, kept piling in all this stuff into her feed. And, it showed up on like regular news. And she's like, this is awful. Why am I seeing all these things? And I said, well, you're seeing them because you keep clicking on them. So stop clicking. I mean, we all know bad things happen in the world, but we don't really need to see that much of it. Other things, Facebook itself influences how content is distributed. And if you've been paying attention the last several years for Facebook or the last few years for Twitter about this, there's been a lot of concern about who is curating who sees what content. Now, depending on your point of view, you might think that the way they do it is wonderful or awful or somewhere in the middle, or maybe you just don't care. But the fact is they are out there doing it. Facebook, Twitter, these other social media things, yeah, they are deciding to some extent who sees what. So if you've heard the term shadow banning, for example, there's that. Okay. Now, the technical elements of a content management system are a challenge, right? Even if you had mostly static data, a lot of data that never changed very much, if you had that batch of data at the scale of Facebook and you tried to deliver content quickly to everybody who wanted it when they wanted it, given that Facebook has, at any given moment, many millions of connected users, that all by itself would be a big challenge. And of course, planning for growth, right? Because people are still uploading photos all the time. But the fact is, Facebook has set it up so their system is a lot more dynamic than it was initially. And so that becomes even more complex to manage. So, first of all, with feed, of course, there's a continuous flow of new, most recent data. And like we talked about the other day, because Facebook tends to prioritize more recent information, more recent posts at the top of your feed, it has to manage this continuous flow of what's new and what isn't. Also, Facebook way back when didn't have real-time updates, comments, edits, stuff like that. Now, if you're participating in some kind of message thread and you're typing a comment, whoever owns that thread will see someone is typing a comment, right? And eventually they'll do it. And you can have many people potentially typing in comments at the same time and get those notifications. And even stuff like if Facebook determines that you're especially good buddies with somebody on there and your special good buddy makes a post and Facebook says, hey, they just made a post, maybe you want to go check it out, you'll see notifications for that right away too. All right, so all that stuff, just the takeaway from that, it's not an easy thing. It's a challenge, and managing the real-time aspects of it, you need to set up some some faster ways to do these things. We'll come back around to that at the end of the lecture. So one particularly challenging case is where content is both very popular and very bandwidth intensive, right? So imagine that Facebook got repeated requests to download a large file. Like there's some video and it goes viral and everybody's posting it and everybody wants to see it. And there are many, many people on Facebook all looking at this video at different times. If Facebook only stored that video in one place, it would be about impossible to keep up with demand because the time required to read and batch up and send that video out, you would have to do that from scratch for every request, especially if the video were stored on disk. The video were stored on disk, there's no way it could keep up with that demand, right? Because requests for it would come in way faster than Facebook could actually access it off the disk. So, two-part solution for problems like that. Number one, caching. So caching, of course, popular data gets put in RAM. But even RAM, though it's really fast, if the file is big enough and popular enough, even RAM is finite and could potentially be overloaded, especially when you consider the networking aspects of it, that it has to push that file into the network before it can, start reading it again and get the next request. So the other part of the solution is replication. Replication means they make multiple copies of it, either at one data center or at multiple data centers around the world if it's really popular. And that way, Facebook can process many, many requests for the same data in parallel. Okay, so that's a fairly concrete example of why caching and replication are important. Now, I'll take it. If you're interested, this is a little bit of an older article, but not that old, how Facebook manages broadcasting live video to millions of people at once. Interestingly, live video is actually much easier to handle, and I'll explain why. It's much easier to handle than a bunch of staggered requests staggered in time. And this isn't something that's on the exam. This is just like special bonus knowledge that you can go do something with over the weekend. I don't know. So suppose Facebook has a popular video, okay? Gets many requests for it. Well, what happens is it gets sent, the request comes in from many, many users. So I'm going to draw some routers, and all those routers are going to reach their end users. We don't have to be super concerned about it. But if Facebook has a bunch of people that are tuned in at any given time, Facebook is going to know that the requests have come in from such and such router and go out through such and such router to reach those viewers. But the thing is, Facebook only needs to push out the video once. Because why? Because it gets to this router says, oh, I need to kick it out to all three of those. So it pushes out the video content on a bunch of different server ports going out or router ports going out to those ones. And those ones do the same thing, push out that data on all their different ports, to any different destinations that get it. So if you're doing live stream, everybody's getting the same data at the same time. So Facebook only has to push it once to get it here, right? And then these other guys, they all push it on their own on these outgoing links. And then all of these guys, they push it out to their people. So each device that's involved only has to send out the video once, as long as they're sending it out on all the relevant ports that are involved. Okay, and you could draw another tree like this going off somewhere else for Facebook and so on. So this is what's multicasting, and it's a much more efficient way of getting data, and it works if everybody's getting the same data at the same time. Then again, Facebook only has to push it out once. All right, so that's something. By the way, if anybody has any questions, concerns, points of interest, whatever, just go ahead and shout them out. We're not real fussy. Okay. Anyway, next topic is cloud. So of course, Facebook has at least several exabytes of photo data, which is way too much to store on a single hard drive or computer, right? You're not going to build like once. I mean, I guess it's technically feasible that you could, but yeah, they're not going to do that. On top of that, simultaneous connections for millions of users, massive read-write requirements, right? Those readers those Facebook users are pulling data all the time. Every time one of them joins up, Facebook has to construct the feed and deliver it to them. Many of those users are doing actions on Facebook that have to be recorded, whether it's uploading photos or making posts or sending instant messages. And of course, all that needs reliability. All that data has to be stored and fairly instantly duplicated so that Facebook doesn't actually lose it and make the users upset, right? If you try to upload some photos and Facebook says, whoops, sorry, we lost that one. Yeah. So of course, once in a blue moon, data does get lost. Like the last time I remember, they had some data center in Belgium. I think it was Facebook, maybe it was Google. Some data center in Belgium got hit by lightning like 4 times within a minute, and they lost like a tiny fraction of their data. So yeah, it's not a zero probability event. You could always have the pieces of hardware that it's stored on all fail in the same way at the same time, but it is pretty unlikely. Okay. Now the solution of this, because there's way too much data to store on a single machine, is you store that data on multiple machines, but you provide outside users with a single interface to reach those machines, right? So as a Facebook user, your data is sprinkled on any number of machines behind the interface, but you go to facebook.com and Facebook controls the process of connecting you to the server that the application you're using runs on and connecting that server to whatever databases it needs to pull the data that you need to get your feed. Okay, so when I say here the operational requirements are broken into segments and allocated to computers, all the different things that you want to do, Facebook takes that one big set of tasks and allocates them over different machines. So it's basically like that MapReduce problem we talked about before at the end of the photo management lecture, where it said we have this big stack of tasks, right? We want to search a stack of documents for some matching text. And instead of having that whole big stack of documents searched by one machine, we give a slice of the stack to each of many different machines. That way they can work in parallel, return the results much faster. Same kind of thing here. When Facebook is constructing the feed, they have a bunch of different database requests sent out to a bunch of different machines. They work in parallel at the same time, pull data back, it gets constructed back and delivered to you, the user. And of course, because it's cloud, all those details get hidden from users, both for security and ease of use. So one thing, you don't want bad guys on the outside knowing what data is stored on what particular machines, right? That would make it much easier for them to target any particular person or kind of data they're looking for. So for security, yeah, you don't really want people outside of Facebook to know where stuff is stored. And of course, for ease of use. Imagine what a pain in the ass it would be if whenever you went to Facebook, you had to specify the particular machine that a particular photo was stored on. It's like, yeah, I want to look at this, my vacation photos in my folder from 2017. I think those are on machine AB12C54G. Yeah, forget it, right? All right. Now, so we've mentioned the cloud, but some of you may be asking, what is the cloud? Well, Basically, the cloud is a bunch of servers connected to some back-end database machines, so a server network with number one, a shared interface. So if you are a user of this cloud system, you go to that interface, like facebook.com. Number two, there's load balancing capabilities because you don't want, number one, you don't want individual servers to get so busy that their performance slows down a lot, but you don't want to have to keep all your servers on all the time because that wastes electricity and makes it harder to do routine maintenance like upgrades and patches and data checks, stuff like that. So you have load balancing capability to make sure that servers don't get too busy, but you have an idea of how many you need at any given time as well, and the ones that are offline, can do whatever. And finally, backup systems. Any data that goes into the cloud needs to be backed up more or less instantly, so you have to have systems to do it and additional storage capacity to put it in. Other features, typically cloud systems are geographically distributed. They don't have to be. It's not like a definitional attribute of a cloud, but yeah, I suppose if it comes to that, load balancing isn't really a definitional attribute of cloud because you could have a very badly performing cloud system, but at this point, because load balancing is necessary, you're going to find it there. Other features, security. Security has to be much higher on a cloud system than it is on, say, your own personal machine, right? If you have a laptop, you get latitude to pick whatever password you want. It could be something stupid like password or 12345, or maybe you don't even have it password protected, so you have that. But Facebook, they're going to put in stuff like you have to have your password such and such. I feel like at some point they should require people to change your passwords, although they still haven't done that yet. What else? There's multi-factor authentication is a possibility there. And of course, just they're more careful with what they do, right? You guys, you might go to some random website that is kind of sketchy and tries to put some malware on your machine. The guys behind the scenes at Facebook, they have to be a lot more careful about that. All right. Now, next question you may be asking is, well, okay, I kind of have an idea of what cloud is, but what's a server? Well, a server is just a machine, a network computer that delivers data to users. So I'm going to show you a picture of an actual server. Let's see if we have this here. Server hardware. Bum, bum, bum. And it basically looks like a flat box. Oh, this is the one I want. Yeah. It looks like a managed switch. They kind of look like this in the back. So they have a bunch of ports, and ports are where they can connect different devices to different devices. That's actually a switch, so not a server. But if you think of a flatter version of that, like something like what's in here, this is these are what servers are. So they call them rack servers. They mount them up in racks like shelves. Yeah. Okay. That's what servers are. Excuse me. And typically the way they're implemented in cloud is as a device, an intermediary between some sort of database system and the users who want to get the data. Now, in principle, any network computer could take on the role of being a server, which means any computer that has a network connection, some other computer could potentially ask it for something, and the other computer could say, yeah, okay, I got that, here you go. And that was basically the model of Napster. I think you're probably all too young to have used Napster. Maybe not, but certainly I'm going to guess a lot of you have heard of it. What Napster was an application where you could basically do copyright violation for music, for MP4s, stuff like that, MP3s even. So what people would do is they would advertise, hey, I have this stack of songs. Anybody who wants it, connect to my machine and I'll send them to you. And Napster provided the mechanism for delivering that data over all the computers that were participating in the system. Now, of course, in practice, servers are actually sold as specific kinds of dedicated hardware. An ordinary business is not just going to go down to Best Buy and buy a bunch of laptops and use them in a server role just because they can. They buy special hardware that is optimized to work as a server and deal with hundreds or even thousands of connected users. So server machines do tend to be much more powerful than the typical client machines. Client machines are like the ones that you and I use, desktop, laptops, smartphones, stuff like that. In particular, server hardware is specialized to handle parallel operations for lots of users at the same time. So they tend to have a lot of cores and a lot of processing power. All right, so that's what servers are. if you like, you can just think of them as very, very, very powerful laptops, although there's more to it than that. All right. Now, picture of cloud here. So this is an old picture, and you can tell it's old because it has load balancing as a separate thing. So we have some users on the left, and they're doing things like HTML, they're doing web browsing, that dude with the envelope, he's checking his email, and they all go to some site, okay, www.whatever. That's the cloud system, right? That's the interface. If they want to get to this cloud system, that's where they go. Now, behind that, there's a firewall, which helps prevent bad guys from peeking into the system. There's a load balancer that looks at how busy all the different servers are and connects the user to, number one, a server that actually has the stuff they need, and number two, isn't too busy at the time, right? If a server starts getting to be too busy, they'll bring some other ones online, and other people might get connected to those in the future. Over here on the right, we have what are called cloud instances. And the reason why I showed you the server is you can see that those little flat boxes there, those are all supposed to be servers. So they're just, each cloud instance is a stack of servers that users can connect to. And then somewhere behind there, they're database machines that those servers themselves will connect to. Okay, that's how that works. Now, what's running on those cloud servers? Well, number one, bunch of applications running on in parallel. So typically what happens, best industry practice, for any one server, you try to have it only run one application. If your budget is really strapped, yeah, you might run multiple applications on one server, or if performance isn't a big concern, yeah, you might, but if your system is big enough to have bothered turning into cloud, you're probably going to run one application, potentially for many users, right? But one application on one server. So you might have one server managing like 500 people using Microsoft Excel or something. Reason why you do that, provides better security, because if everybody on a machine is using the same application, the data packets going back and forth from the system are going to look about the same, and it's much easier to detect something that looks out of place. So just you have a larger supply of baseline data, your automated security tools, they'll have an easier time spotting if something goes wrong. Other stuff, a big one is better quality of service management. So quality of service, that means how well the system is running. And if you have a lot of different applications running on one server, then it's kind of up in the air what's going to happen if you increase the number of users. So simple example, suppose you have 200 users connected to a server. 100 of them are using Microsoft Word, and 100 of them are doing video streaming with some application there. If you add on 100 new users, oh, I should mention, Microsoft Word is very undemanding in terms of system resources. Basically, you take the file and you look at it, they don't have to worry too much about it. Continuous real-time video streaming is very demanding, right? There's a lot of data going back and forth. Now, if you add on 100 more users to that server, if most of them are using Microsoft Word, the added load is going to be negligible, right? It's going to be like a rounding error for the video stuff. On the other hand, if most of those users are using video, you're going to be about doubling the load, because that Microsoft Word action, that'll be basically a rounding error. So if all of the servers are just running one application, then you have a pretty good idea that if you scale up the number of users, the work that the server has to do is going to scale up, and you can predictably say, oh yeah, the server is going to be pretty busy. It's time to bring on some new ones to do the same application. Okay, so quality of service is a big thing too. Anyway, the way the system's going to look at it, it says, how busy are these servers? Well, one of the things that's going to get measured is computation requirements. So if you've ever done the task manager in Windows, you can see what percentage of the CPU capability is being used by different applications. Yeah, they kind of look at that. So some applications are going to require the CPU to do a lot of work, others not so much. And the other two things, network transmission capacity. Is there a lot of traffic going back and forth from the server to the clients, or back and forth from the servers to the database? If that's getting to be too much, then yeah, again, you time to bring on some new servers. Okay, thin versus thick. So there are two kinds of clients and applications, both called thin and thick, so don't be confused. So for clients, thin means the machine is relatively weak. So you might think of that like a low-end smartphone at this point, for 2023. A thick machine is one that's relatively powerful. Like maybe you spend like $5 grand on an Alienware desktop. That's probably a pretty powerful machine. Okay, so that's what we mean in terms of clients. Thin clients are weak. Thick clients have a lot of power. All right, but it's all relative, right? What's weak today would have been super crazy powerful in 1998. So again, this is all just relative. Now, in terms of applications, there's two kinds of applications. Number one, the thin application. A thin application means most of the work happens on a server, not on the client machine. So the server's job is basically to send requests to the server and process and display whatever data the server has back. Okay, so an example of that would be, I don't know, again, some kind of heavy number crunching. Oh, well, Facebook is a good one. I'll just leave it at that, right? You go to Facebook, it's not like Facebook sends you all the data you need to construct your own feed, right? You don't have that stored on your machine. You send a request to Facebook, says, hey, I'd like to check into my account. Facebook just says, okay, here's the web page, here you go. Look at that as a thin application. Now with a thick application, the processing mostly happens on the client machine. So an example of that, you say you score a copy of SAS, statistical analysis software, and you decide you want to do some heavy-duty regression analysis on this massive batch of like 10 gigs of data. It's going to do a bunch of number crunching there. All that processing going to happen on your machine, right? That would be an example of a thick application. Now, in practice, for business, most systems either have thin clients running thin applications or thick clients running thick applications. Reason is this. If your machines are weak, if they're thin clients, they're not going to have capabilities to do very powerful thick applications. So it makes sense to let the servers do most of the heavy lifting and run thin applications on them. On the other hand, if you have thick applications, if you've shelled out that money for these powerful machines, then yeah, you do have the capability to run, really demanding thick applications. Okay, in which case, the flip case is if you try to run thick applications on thin clients, you'll be very limited in the range of applications you can run, right? Because your clients just don't have a lot of power to run very much. On the other hand, if you have thick clients and you're running thin applications where the work mostly happens on the server, you might fairly ask, why did we spend all this money on thick clients when the servers are just going to do the work? Okay. All right. So next stuff, ACID properties. Now, databases in general do try to ensure that queries receive correct and current data. But relational databases in particular tend to be set up so that you always have a guarantee that you're going to get correct and current data. And that is implemented through what are called ACID properties. So ACID stands for the four properties: atomicity, consistency, isolation, and durability, which we'll talk about in a moment. But the point of those is to make sure that your database is always up to date and any question you ask it always gets the correct answer. So it is possible to set up a relational database that doesn't follow ACID properties, but it would be very unusual, okay? And we'll talk about in a little bit, it is also possible to set up a NoSQL database that fully follows ACID properties, but in some ways we'll find that that's not always the case. ACID properties are one of the corners that get cut with some of these NoSQL systems. All right. So first one, So consider a hypothetical example. You have just updated your Facebook relationship status to "it's complicated." All right. So first property, atomicity. Atomicity means if you have a group of related database actions, either they all happen the same way or none of them happen, right? The goal there is to make sure that after this operation gets processed, that all the signs in the database are pointing the same direction. So if you try to update your status, either number one, it goes, and a relationship status update like that, remember, it's automatically going to be backed up. So there's going to be multiple copies of it, right? So it's going to try to first accept that in operation from you, and then update all the backup copies of your relationship. If any of those operations fails, they'll be left in the original position, which means if some outside user came along and said, hey, I wonder what the relationship status is, they might look at one of the ones that's out of date and get a wrong answer. So atomicity, reason why that's in there is to make sure that everything involved in a database operation looks the same way afterward. Okay? Okay. Second one. Oh, and if it does, right, if it goes through, great, all the backups get updated. If any one of the attempts to update a backup fail, then of course you'll have that wheel spin around for a little while and it'll eventually say, sorry, we were unable to complete this request. Please try again in a few moments. Second one is consistency. Consistency is kind of a weird one because the way they talk about it in technical database talk, they say if a database starts in a consistent state and processes a valid operation, it will end up in a consistent state. Well, what that just means is that the database has to follow its own rules. So if you've set up some set of rules for your database and you have an operation that can be processed, it should lead to a state for the database that still follows those rules. Okay, so for example, one rule in Facebook is that, the default setting, people who are not your friends cannot look in and see much about you, right? They won't be able to see your relationship status, for example. So if you process two actions in order, first you say, I'm going to unfriend someone, and then B, I'm going to update my relationship status. That person you just unfriended should never see the relationship status update because they were unfriended beforehand, right? That's an example of consistency. And there's different ways to provide it, but again, actions processed in sequence and according to any rules in the database. So if you start out consistent and you do some operation on the database, it should still be consistent afterward. All right. Isolation basically means that any database operations sort of happen in a little isolated self-contained bubble and they get processed the same way regardless of what else is going on in the database. One way to look at that is to say that operations on the same data don't interleave, right? They don't cross over and interfere with each other. So I'm gonna give you an example. And it's related to atomicity. That's okay. Okay, so you do your status update. All right, and you send that to Facebook, and Facebook is very happy to get it. And then afterwards, someone looks at your status. Okay? So this is our sequence. Now remember, part of processing the update is this automated backup. So there's automatically, any copies of your relationship status are going to be updated. So I'm going to put this in a little bubble here, a little bubble of green goodness. What you don't want another user to peek in while the operation is still pending, right? Because while it's pending, some of those copies of the relationship status might have the old information. So isolation means that the state of any data still in operation, well, still being updated, cannot be seen from the outside. Okay, and that's another way of ensuring ACID properties where the outcome that anybody looking in at your system is always going to get the correct answer. If you say, well, there's an operation going on this, you can't see this at this very second. We'll send you that information when this operation is done, and then you can peek in and see it. Okay, it's another way that you get prevented from getting bad data. All right, last one is durability. Durability is very straightforward. It just means once an operation is processed by the database, it's not going to be lost. It's going to be permanent. So in the case of systems, they're going to make multiple backup copies of whatever. Even if one system crashes or the RAM goes bad or loses power, whatever, you're still going to have a record of that change somewhere in the database that can be recovered. Now, of course, durability is never 100% absolutely certain, right? There's always a possibility for some weird low probability event where a bunch of hardware fails at the same time. Sure, that could happen, but it's also very, very unlikely, right? So durability doesn't mean that it's absolutely never going to lose anything. It just means that losing something is going to be a really, 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 really low probability event. Okay. Now, as you might guess, following acid properties can inhibit performance, meaning your system is going to slow down. So, for example, if you have a very large system with lumps of popular data, users may often have to wait on operation. So, if you didn't allow the possibility of multiple users commenting on a post at the same time, imagine if you had to wait for everybody ahead of you to finish with their comments before you could get yours, right? And that might be something you would have to do if you say, well, this record consists of, this entry followed by this entry followed by this entry. Nobody would like that. You can also have the possibility of what's called deadlock. So I'm going to do a simple example there. Suppose two users, Al and Bob, are attempting to update records U and V. And Al is doing the sequence update U, then V, and Bob is doing the sequence update V, then U. Okay? Remember, we're insisting on acid properties here. So Al starts his, he makes a temporary change to U at the same time as Bob makes a temporary change to V, right? A prospective change. When Al then tries to update V, it's going to see that V is locked. V can't be dealt with by Al because why? Because Bob is working on it, right? Likewise, when Bob's operation attempts to access U, that can't go forward because Al is still working on it. So these two database operations, they're blocking each other for from completing, and they'll eventually time out after a certain long time. Now, another case that could happen, imagine if you have a very, very, very large database table, and users frequently query that table, ask it questions about this or that. In a strict acid property system, anytime somebody updated part of that table, you wouldn't be able to run a query on that table. Because why? Because some change to a record might have changed the query results, so you got to wait for that update to finish, right? But if there are a lot of updates going on, the queries might never be able to happen. The system might be doing all it can just to keep up with the updates. Likewise, if there are a lot of queries that take time, the updates might have trouble getting time to do it, right? Because they all have to happen sequentially. So it's a big hassle. Anyway, so there's also the case that it doesn't always matter whether there are mistakes in the data, discrepancies, conflicts, call them what you will. For example, imagine if you have posted a photo to Facebook and it is currently located on two different data centers, okay, because you have friends on both sides of the world. It really doesn't matter that much if one side of the world sees that there are 10 likes on that photo and the other side of the world for a little while sees that there are 11 likes on that folder. It's not like they're both going to look at different ones at the same time and get all mad and call up Facebook and say, hey, this is bullshit. He's got 10 likes here and 11 likes here. What are you doing? I want my money back, right? There's what money, right? So yeah, there's some stuff that it really doesn't matter if there are some discrepancies in the data between one copy and another. And in cases like that, holding on to acid properties is more trouble than it's worth. So Facebook, in many cases, has chosen a policy of what's called eventual consistency. Doesn't mean that everything's going to be perfect right when everybody looks at it, but it does mean that, yeah, eventually the system will catch up with whatever's going on. There'll be some batch operation, anywhere 10 seconds or a few minutes down the road. Facebook will synchronize those two data centers, right? But they're not going to be doing it constantly every microsecond. And some users might see different information until then, but, it's going to be information that it doesn't matter if there's a discrepancy. All right. Now, one example of this is the key value store. So Facebook often uses database models that prioritize speed over accuracy, right? NoSQL, which stands for Not Only Structured Query Language, is an umbrella for a bunch of different approaches that are mostly either designed to help the database run faster or to be flexible or to make better use of available storage capacity. So with NoSQL systems, they have more flexibility. They're not tied down to that relational database model of having a field for any field in a table, it has the same size in any record, right? We talked about that the first day. They don't necessarily follow that. They're also, because of that, they're better at accommodating different data sizes or different structures, right? For example, in a NoSQL database, or like this key value store we're going to talk about, is one approach to packing data in really tightly into storage media, right? Which again, if you're talking about you have one field designated in a table to store a whole video, some videos, yeah, use the whole space, others only a tiny fraction of it, you're going to waste a lot of storage capacity. Last thing, auto sharding. So different relational databases, as long as you can pull all the data and store it in RAM, it's going to be pretty fast. But with auto sharding is the idea that the performance of a NoSQL database can potentially be about the same even if you have data stored on a bunch of different machines. The way this typically works is if you say, well, my database is essentially going to be a list of objects, and I find what particular object I want that's going to be located on any machine, and I just pull it, right? It's not a question of taking the entire contents of the database and putting them into RAM. Your database is maybe designed to only pull one thing at a time, like with photos. All right. Now, over the years, Facebook has designed or adopted a whole bunch of NoSQL systems. You don't need to know these for the exam, but if you're mildly interested in this, you can go check it out, see what they're all about, how they work, that sort of stuff. And Facebook isn't totally on the NoSQL whatever bandwagon. They use some standard relational databases as well, like one for wall posts. So when people just post something to their profile, yeah, it can have a slight variability in text, but they tend to be roughly the same size. There's not a huge amount of space wasted there. And even if people are putting things like photos in their wall posts, Facebook doesn't actually keep the photo in that record. What it does is it keeps, a link to where that photo is stored. So a relational database, maybe it's not the most efficient way to do it in terms of storage space, but it's efficient enough and the speed factor helps. All right. Now, the way a key value database works, number one, every value, so every record in the table has a key, just like the key field in a relational database. Beyond that, the database doesn't enforce any structure on records in terms of fields or formats, which means every record in a key value store is like its own custom database. Every record can have a completely different format from every other record in that. And where that sort of system makes sense is if you have one database that's being shared by a bunch of clients that all have different data storage needs. So the different features on that, number one, because it's built into the system that every record could have a different format, changing one object's definition, one record's definition, doesn't have any effect on any other objects. It's not going to hurt them. Number two, it's scalable because you're only pulling one record at a time. You're not generally doing like big queries through the whole table to find stuff. It's easy to have that database run on multiple machines without suffering performance loss. Speed, in a variety of ways, if you have a lot of data in there that doesn't need to follow ACID properties because it's not super important that it's all totally perfect, then yeah, you can optimize speed. You can cut various corners to help out with that. But like anything, there's no free lunch. There is a cost. And the cost here is that you can't do table joins. Well, you can't easily do them. So a table join is just a query that spans across two tables. Now, what we talked about before is that if data is stored on multiple machines, or anytime you're doing a query in a relational database, you're looking to see if, you have to check all the fields within a table and see if they match with whatever the query criteria are. But with a key value database, you not only have to look inside each record, but you don't know where the stuff is or if it's even there. So basically every record, you have to do a lot more work to find it. Even if there's a header at the start of the record that says what's in there, you have to check that and cross-check it and then find. There's another layer of work. And if all that is on multiple tables and those records are on multiple machines, doing that kind of query is going to be super, super slow. So you don't want to do that. All right. But where key value pairs make the most sense, number one, if you have objects that inherently don't have a definite form or structure, right? Like web pages. Some web pages are short, contain very few images, web objects, any of that stuff. Others could be very large, lots of text. Facebook user history, if you're storing that as a blob of data, that would mean, a new user probably doesn't have much history at all. But if you're somebody who's been on Facebook for like close to 20 years and you've been a very active participant, then yeah, there's going to be a lot of data there about you. There are other objects that just tend to consume a lot of space, like videos and images, and thus it's generally much more important to store them as compactly as possible than it is to, efficiently reach large groups of them or run queries on them. There's a reason why Facebook doesn't let you run queries like, show me all the photos posted in October 2018 by people in Chicago. The database just isn't set up for that. And other times you can have applications that generate unrelated data used together. So, for example, if you have a security application that uses log files and cached application data, the different combination for every application at every given time with a different security tool, it could have a very different outcome format. And again, it's inherently not going to have a standard format. You'd have to have a separate table for every one of those things. And if you have a separate table for every one of those, then when you're writing your SQL code, you need to separately refer to every table. It'd be a big pain. All right, so 1 minute about market status, and then I'm going to talk a little bit about the exam, and I'll try to get out of here just a couple minutes after. Okay, so this is a bit of an old image, but it's the best, most recent image I have for this. And it shows how much people are spending on these things. So relational database is green. You'll see that that is growing slowly but steadily. On the top, you'll see a combination of Hadoop and NoSQL, which is the black bar, which is becoming an increasingly large chunk of the black and blue combination at the top. Likewise, other non-relational becoming a smaller chunk, but still there. Now, the takeaway from all this, you have to remember that this is how much businesses are actually spending. This doesn't count internal usage. It doesn't count Facebook using its own systems, Google using its own systems, YouTube using its own systems, right? These are outside businesses. So if you're some business that your thing is managing invoices and customer data, stuff like that, yeah, you're probably doing that in a relational database system, and that's continually growing. But where we see the growth for these other ones, if you're storing data that doesn't have a determinate form, like copies of web pages, copies of other documents, maybe promotional video content, things like that, that's probably what you're going to store in some non-relational database. And we're seeing steady growth with that. All right. So there's that. Anyway, what I want to talk about the exam very briefly. So, okay. So the 4 kinds of questions you will see on the exam. Yeah, if you're leaving, you do want to check this out after. So number 1, terms and definitions, right? So I have said this is not a terms and definitions class, but terms and definitions questions are really easy to write. So there are always going to be a few of them in there. So basically, anytime you're going through these topics of interest or going through the slides and you see a term and you don't know exactly what it is, figure out what it means, okay? Second thing, similarities and differences. Anytime you see a group of related concepts, for example, different memory types, right? Know how they're similar, know how they're different. What's the difference between volatile and non-volatile RAM or non-volatile memory? What's the difference between the various types of RAM, like synchronous and static? Things like that, okay? So anytime you see a combination of those, what are these things? How are they similar? How are they different? Next one, typical usage, right? So for example, we talked about RAID devices. We talked about mirroring, we talked about striping, we talked about parity. What are they used for, right? So mirroring, you could say, well, I know what mirroring is. It's where you have multiple copies of the data stored on different disks in the device, but why do you do that? Okay. And then the last one, system changes. Okay. These are rare questions, but there will be a couple of them. Now, system change will be like, you have a system like this. For example, we talked about these hybrid RAM and disk systems. You have a system that's running entirely in RAM. What would be the probable change if you switch it to a disk-based system? And the probable outcome would be, well, it'd be a lot cheaper, but it would also be a lot slower, right? So something like that. Now, these system changes questions, if you're good with all these parts, they tend to be pretty easy, right? If you're not so good with them, then yeah, that's a problem. So where this leads, part 2, how to study. Okay, so first, know the terms and definitions, right? Because you never want to miss that low-hanging fruit. Those are the easy questions. Number 2, for any term or concept or technology, think about what is it? That's mostly terms and definitions. How is it used? And why is it used that way, right? If you take a little bit of time and think about the material this way, you'll be a lot better off than if you just try to memorize a long list of terms and definitions, okay? So cramming for this sort of thing, probably not going to work too well. Get a head start. Okay. Does that make sense? I hope it does. All right. That's all I got for today. Good luck. Having a nice weekend. Drive safely. All that. How may I help you?
So, the backpack, I know on the syllabus it says 2 responses